Very good. Yeah, hello everyone. Today we continue our course on quantum computers and quantum technologies, and today is the lecture number 10, I guess. So last week we started discussing the IBM Qiskit. We learned how we can simulate the quantum circuit of arbitrary complexity, and basically using two approaches: the classical one, which just mimics the operation of a quantum computer, and the second approach was we are sending the projects to IBM, real IBM quantum computer. So today, let me what is all right, so today we will discuss the interference in quantum physics, and basically why we need this interference. And we will talk about Golden Single Qubit Circuit. Let's call this Golden Single Qubit circuit, and Ramsey Interferometer. Ramsey Interferometer. So it's crucial that you understand today's lecture. So if you got any questions, please don't hesitate to ask me any that probably pop up. So the first concept we discuss is the concept of interference. Oops, let me change the color to the black one. Interference. So you probably remember from the course on basic physics or wave physics, or maybe optics, that interference is a phenomenon that occurs when two or more coherent waves interact and combine with each other, right? And this combination can be either constructive or destructive. So let's actually write this down. So the interference is a phenomenon that occurs when two or more waves intersect each other and combine with each other, and combine with each other, either constructively or destructively. And this interaction, right, this interference results in interference pattern. So what does that mean? So let's first recall from optics, like a typical experiment when we have let's say a screen like this, right? And a light source somewhere here. So this is our source, light source. So this light source creates the bright spot, right, on this screen. So this is our screen, and this light source creates a bright spot like this, distributed like this, with maximum in the center and gradually decreasing outward. And so we basically can characterize this light spot by its intensity. So this envelope is intensity. Let's denote this I with index 1. This is the intensity of the first light source. And if we denote this coordinate by x, then my intensity is a function of x, right? Different coordinate is assigned to different intensity. But we also know that the light is actually a wave, right? And if we take another equipment measure, we would be able to measure, for example, these oscillations of electric field. So the electric field will be distributed something like this, and it would be electric field of the first source as a function of x. And now, if I write the formula for the electric field of the first source, so we have just one coordinate and our field is scalar, it would be something like the square root from the intensity, right? And times the phase factor, which is e to the power of I kx, and k is the wave number, which is either omega over c or 2 pi over lambda. Yeah, so why this factor here? Well, simply because I require, or I normalize my units. Let me admit the guys. Very good. Why this prefactor? Simply because I use the units where when I take the absolute value of the electric field squared and I get what? And I get this intensity of x, and then e to the power of I kx times e to the power of minus ekx cancel out, so I get 1. So I normalize my electric field so that the square root, the square of absolute value of this field gives me the intensity. So the intensity is the envelope of my light source, and this electric field has its phase, right? So now let's suppose I have another light source somewhere here. It can be the same source, just shifted by some distance or so. So this is my source 2. That one 1. This one is 2. And for this light source, I can write basically the same function, x square root of 2 as a function of x times e to the power of I kx. So everything is just the same, but some additional phase. So this phase comes from the fact that we shifted the source or we somehow changed the source. It doesn't really matter. So I suppose that the second source gets this additional phase difference comparing to the first one. And similarly, the intensity of this second source is just the square root of absolute value of the electric field. Very good. So now I go ahead and consider both of them. Consider their both fields. What I get? My total field will be the sum of first and the second one. So the sum of these two partial waves. And for the first one, I have the square root of intensity times e to the power of kx. And for the second one, the second intensity, square root e to the power of I kx plus phi. This is for the field. So we just sum up all the fields. This is the superposition principle, right? For any linear system, the solution of is the sum of partial solutions. And now let's calculate the intensity of this total field from both sources, right? So it will be this I1 to the power of kx plus a2 e to the power of akx plus phi modulus squared. So so this is the modulus square of the first one, which gives me I1, plus modulus square of the second one, which gives me I2, right, intensity of the second source, and plus the first one times the complex conjugated second, and vice versa, which gives me square root of I1, square root of I2, and e to the power of minus I phi plus e to the power of I phi, right? Simply because e to the power of I kx times e to the power of minus e kx minus e phi, these two cancel out, and I get the e to the power of minus I phi, and the same one for the fourth term. So now I recall this. I mean, I recognize that this is actually the real part of the exponential function if I divide by 2 and multiply by 2, this is the real part of e to the power of I phi, which is, according to the Euler's formula, cosine phi. Right? So I conclude that the absolute value squared of the total field is equal to I1 plus I2 plus 2 square root of I1, I2 times cosine phi. Very good. So and this is nothing but the intensity of the total field. Right. So the intensity of the total field is not just the sum of the intensities, but depends on the phase difference between first and second light source or source of any waves. The same works for acoustical wave or for any types of waves. So for now, let's consider two ultimate cases, right? So first of all, the in total intensity for the minimum of total intensity, minimum, is what? So I assume that I1 is equal to I2 for now. So the intensities are the same of both sources, and the total intensity minimum, because cosine is a function that, I mean, from -1 to 1, right? So the minimum will be when cosine is equal to -1. And when cosine is equal to -1, the minimum intensity will be 0, provided that the intensities of first and second source are the same. And intensity maximum will be when cosine is equal to 1, and in this case it will be 2i plus 2i 4i. So we conclude that in the case of interference, the intensity oscillates between 0 and 0 and 4i. Without interference, we would have a constant intensity of 2i, because it would be I plus I. So it's just sum of two intensities. Right, so interference gives us this interference effect that creates interference pattern, and how it looks at the screen. So let's suppose I return to this screen I had, and without interference, this intensity distribution would be this one. So it's just I1 plus I2. So it's no interference. But with interference, I have this cosine phi, which oscillates as a cosine function, right? And also overlapped with this envelope function. So it would be something like, something like this. Right. So the maximum intensity total with interference at the maximum would be 2 times larger than the maximum intensity in the case of no interference. So what? So this is important for this area of interferometry. Interferometry. So what is interferometry? Interferometry basically the approach to measure something or detect some variations, basically for sensing, that uses the fact that pattern depends on the relative phase. So interferometry use the fact that interference or interference pattern significantly depends on the relative phase. And we use it for measurements and sensing. And for many other different approaches, right? For example, how this noise canceling AirPods, for example, work, right? So they have the additional source of the acoustical waves coherent to the ambient noise or ambient sound. So they measure that sound and generate the source in opposite phase to make this cosine phi basically equal to -1. And that results in the destructive interference at the human acoustic sensor, right? And that creates this noise canceling effect. Or I mean, many different approaches and technologies use the same way to cancel destructively cancel the wave effects somewhere. So now let's consider this screen like a piece of glass. So this is just a surface of some glass, like a window or something like that. And we consider a light wave. Again, it can be acoustical wave, any wave of any sort, of any kind. Coming to this, impinging this surface, right? So let's consider first the wave picture. So in wave picture, as you know, this wave partially bounces off from the surface and forms the reflected wave. And if this surface is not rigid, this wave can partially transmit through this surface to form the transmitted wave. So this is transmission wave. And for simplicity, let's assume that our surface has the reflection coefficient of 0.5, meaning that 50% of the wave or wave intensity bounce off in form of reflection, and another 50% transmit through the surface. This is how we used to think about all this, right? When we studied these basics of physics, elementary physics, and wave physics, etc. But there is another picture, and since we're talking about quantum, right? So let's consider this photon picture or quantum picture. Photon picture. So you know, photon is a quantum of optical wave, right? We can detect these photons one by one, meaning that the light that surrounds us, the light from any light source, actually comes as a stream of many billions and billions of quants of electromagnetic energy. And for simplicity, we can draw this quantum of light by this spot like this, right? So this light quantum comes to the surface, and what happens then? So this light quantum still has a probability of transfer through the surface, through this screen. And let's say this reflection or transmission coefficient also 0.5. So 50% of light passes through, and another 50% of light bounces off the surface. So the surprising experimental fact is that this picture works not only for like many photons in the system. This picture actually holds for just a single photon in the light beam. You can decrease the intensity of your light source to make it just like light emission of one single photon per time, per some period of time. So your light source is very weak. It emits just one photon, let's say, per second. And one might say, what happens to this photon? Like if your window is semi-transparent, why this particular photon decides to go through the window, and why another photon decides to bounce off from the window? Like what's going on here? The photons are completely like identical, no difference between them, but one decides to go through, one decides to bounce off. And so this is exactly the quantum effect. So like anytime you look in the window and you see your reflection, and you see the like the street outside, this is already quantum effect, because any single photon that comes to the window like decides if it bounces off or transmits through the window. And the point is that for any single photon that comes to this slab, to this surface, before we measure the photon being transmitted or reflected, we have to take into account these both situations, right? This is exactly the same situation as we discussed for a spin, for example. It can be spin up or spin down, but before we measure the spin state, we have to take into account both available cases, both scenarios. Spin is simultaneously up and down until we measure it. And the same happens here. So we don't know if the photon decides to pass through or bounce off. We have, for every single photon, we have to take into account these both opportunities for the photon. And accordingly, we write the this situation as a superposition of two cases.
Dr. Alex, I have a question.
Yes. Yeah.
This case you told about a single photon, it could either pass through or reflect back. Eventually, this is what a qubit is, right? Means we can interpret this as a qubit.
Yeah, and this is what I'm gonna talk about next.
Okay.
So let's assume, or let's write the wave function for the photon before interaction with the surface. So our photon is located on the left side, and so I write this before interaction, before the screen. By the way, there is a very nice book written by Richard Feynman. The book is called Quantum Electrodynamics, or I have this book actually. I don't remember the title exactly, but that's about like fascinating quantum electromagnetics or something like that. And that book is like written in lame words for everyone, and he discusses exactly this situation like in the very first chapter. So before the screen, we write the wave function of the photon like this, right? So my photon is located in the left side. So photon is in the left side of the picture. After the interaction, what happens then? My photon can be on the left side or on the right side. And for simplicity, or to make it like simpler, I assume that my reflection transmission is 0.5. So it's exactly like 50% of probability to be reflected and 50% to be transmitted. So this is the wave function of my photon after the interaction with the screen. So let me rewrite this like this. So I had this state before interaction, and then my final state after interaction is this one. So do you recognize what operation is this?
Hadamard?
Yes, Hadamard operation, Hadamard gate. So basically in optics, any dielectric surface, it would be better to have reflection 50%. So the beam splitter, 50% beam splitter works as a Hadamard gate for any photon in the system, in the stream. Okay, so let's actually write this down. So in the case of light, a simple piece of glass, simple piece of glass creates the quantum superposition. Creates the quantum superposition. So one surface of glass creates quantum superposition. But what happens if we put another surface of glass? Like, suppose we have one surface that creates superposition, and this is Hadamard gate, right? Hadamard operation that we discussed many times. But what if I put another Hadamard gate, Hadamard operation? It will close the superposition, right? So let's suppose I have these two surfaces, surface 1 and surface 2, and I have a stream of photons, and I consider just one photon. So my light source is so weak to emit just one photon. It comes to the surface. It can the same photon. It can bounce off and to be reflected back. It can go through this resonator, right? With system of two surfaces. Then it goes to the right surface. It can reflect back or transmit through. Then from this surface it can reflect and it can transmit. And then here it can reflect and can transmit. The same photon, it can propagate many times like this before it will leak this resonator. And again, before we like make the measurement and detect the photon in either the left side or in this resonator or the right side, we have to take into account all these possibilities like simultaneously and sum up all these partial waves. But what actually happens here is that let's, for example, consider these partial photons or partial waves on the left side. So when we sum up their fields, right? They also have this destructive and constructive interference, depending on the distance between these two screens, these two surfaces. Oh, well, it's very easy to understand, because when I change this spacing between two surfaces, the photon requires like more or less time to propagate within back and forth within this resonator. And if time changes and for the same velocity, the phase changes too. And for some phi, the particular the partial waves will cancel out each other. So, and the solution for this case, for example, can be written like this. So the probability of finding the photon on the right side, let's again denote it by R cat, right? So this probability of finding the photon on the right side of this picture will be something like 1 over 2, then 1 plus cosine phi. And so this is for the transmission. And probability of finding the same photon on the left side of this picture would be 1 over 2, 1 minus cosine phi. This is reflection. So as you can see, changing the phase from -1 to 1, the probability, for example, probability of R, I mean, in finding the photon on the right side, will be something like this. Right. Well, if I count my phase from 0, then this will be PL. And this would be PR. No, vice versa. Right, so the cosine is equal to 1, and yeah, so this will be R and this will be L. Anyway, so the probability changes or depends on this phase, which is simply the distance between two screens, between two surfaces. And for example, speaking about optics or RF, it's like important to mention that in optics or RF also this change of phase, right, is given by the vector, the wave number times delta x. Delta x, for example, the distance between the screens. And this wave, let me write this way. So this wave number is just, I mean, it's a 2 pi over wavelengths times delta x. So the wavelength of a wave is very small. I mean, for example, in optics, it is like 500 nanometers. So, I mean, we even cannot resolve these variations or these objects in a conventional optical microscope. So variation is extremely small, but this variation creates the finite delta phi, and this delta phi variation changes the interference pattern significantly, so we can easily detect this change. And this is the way how interferometers work. You're probably aware of these interferometers like LIGO that detected the gravitational waves, right? So they all based on interferometry. The best sensors ever are based on interferometry, interference effect. Yeah, so since lambda is very small, the delta phi is large, or can be like measurable or finite for very small variations of delta x. So let's write down the algorithm of the interference setup, of the setup. And you will understand why I write so like formal this part. So algorithm for the interference setup. So first of all, we have to open the superposition. Open superposition. By putting the first semi-transparent screen in optics, for example, or in quantum, it is like putting the Hadamard gate on the first place. So the second step is control phase. Anytime you control phase, like for example, if you want to create some sort of sensor, you need to come up with a way how the variation of parameters or of some like figure of merits in your system affects the control phase. If you want to create some something else, like today we will see how the quantum algorithms use this approach. Then we need to come up with a way to control this phase on a at our will, or in the control function. So control phase, and then the third step, close the superposition. Close superposition with another screen or another Hadamard gate in quantum, right? How it looks like. So first of all, suppose we open up the superposition, right, for some photon that comes to the system. This photon, for example, has the spectrum like this. So this photon can be of our light source gets the finite line, the spectral line, so it can emit photons of slightly different wavelengths or frequency, right? And then I open up the superposition for each of the photons. So on the left side, the wavelengths, the wave vector of my photon is ket L. Then when I create the superposition, the wave state of my photon is L plus R. So this is a perfect quantum superposition of a photon. Then I assume that I vary or control this phase inside this this system. My state vector will be something like some function f depending on phi state L plus another maybe function g of f state R, right? And then I close this superposition by another screen, and the photon comes out or bounce off to the left. So it comes out with probability that depends on phi, and my result will be something like this, right? So some spike in the result. So my goal for the given input, I design my resonator, the system when I open open superposition, then do something with the phase, and close superposition to achieve some effects. And in fact, in quantum computing, there are a lot of, or many algorithms that utilize this principle. So basically what they do, they try they intend to control this phase to get the very large spike in the result that corresponds to a particular state. I don't know, something like this, for example. And if you tailor your algorithm, I mean, you can tailor it in a way that this output, this spike, will give you the answer, for example, to some particular problem you try to solve, right? So now we can go ahead to this golden single qubit circuit. Golden single qubit.
Alex, I have a question here.
Yes.
It's related to the above, like the open superposition and the closing one. There will be a point when the photon will go inside and will remain inside, because with every striking, it is losing the energy as well. So is it the case like what I'm talking about? Like
no. So the photon doesn't lose the energy. This is very important like point to understand. So the energy of any quantum, I mean, basically this is why we describe any light source or basically any energy by quants, right? The quanta of energy. According to the Planck, the quant of energy is h bar omega. For our photons, this omega is nothing but the energy, or I mean the frequency of light, or if you wish, the wavelengths of the light. For let's say I have the source of red light, like red light laser pointer. So it radiates this red laser beam. So this laser beam is composed of billions of photons, but their energy is pretty much the same and is given by this formula. If you have n photons, it will be n times h bar. So this is the energy of n photons. What happens when you have a system that absorbs energy? So the system that absorbs energy, what it changes? Frequency or the number of photons? It changes the number of photons. The frequency doesn't change. Actually, frequency is something that is like very difficult to change, and you need some nonlinear media, and this is the subject of nonlinear optics, and you need like high intensities, etc. But when your light is absorbed in some absorbing media, what actually happens, you have absorption of n, the number of photons, but the frequency stays the same. For one single photon, your n is equal to 1. So you cannot change n. I mean, you can, of course, this photon can be absorbed by some maybe impurities or something like that in the system. But we consider the case of no losses. So our photon can be either transmit or reflect. In reality, of course, it can be absorbed, and that makes our system so-called non-Hermitian, right? So this system for now is described by Hermitian operators, Hermitian unitary operators. I mean, it's described by unitary operators, and the spectrum, the energy, is described by Hermitian, for example, Hamiltonian, etc. But and this part of the story is not included to the. I mean, it doesn't take into account in the classical quantum. I mean, in the quantum mechanics. In the quantum mechanics, in order to consider this absorption and other mechanisms that make the system non-Hermitian, we have to bring some other techniques that we didn't discuss and I'm not going to discuss in this course. So we assume that our system is Hermitian, no absorption, and a system without absorption, the photon can be or transmitted or reflected, and that's it. So frequency doesn't change. What changes is the number of photons. For a system of one photon, nothing happens to the frequency. And the result that you see on this side, on the right, is a schematic, like of this the picture of the idea what we need. We need to like design our system, design how we change this phase in the system to achieve a answer that is like correct answer, right? The answer that we need. We will discuss how, I mean, not in detail, but like in very general, how it works in quantum. So does this answer your question?
Yes, I get it.
Okay, so let's return to Golden Single Qubit circuits and the Ramsey Interferometer. Ramsey Interferometer. So we already discussed this Golden 2-qubit circuit, right? The circuit that generates the maximum entangled state or Bell state. For 2 qubits. For 1 qubit, there is another, I mean, I call this Golden Single Qubit Circuit because like you can meet this part of the circuit in many different circuits. I'm not sure if this name is official, probably not. Anyway, so let's consider this circuit. So this is just 1 qubit circuit. I have 1 qubit, right? And then according to this algorithm here, what I do, I open superposition. To do so, I put this Hadamard gate first, right? This creates the superposition. Then I have another gate. We call this P phi gate, right? This gate, which is represented by this matrix 1, 0, 0, e to the power of I phi, right? So it doesn't change the state 0, but it multiplies the state 1 by this factor e to the power of I phi. So it basically depends on the phase, this phi. So I change this phase by this operator p phi, And then I have to close my superposition by another Hadamard. And I'm interested in the result of this. So let's figure out the result. So according to so our first gate is Hadamard, and the Hadamard gate turns the state 0 into state plus, right? Which is 1 over square root of 2, state 0 plus state 1. So this is the first operation. The second operation is this gate PEF. What it does, it leaves the state 0 unchanged, and the state 1, it multiplies this by this phase phase term like this. So this is my state at this point before the final Hadamard. So now let's apply the Hadamard to this final state. Hadamard 1 over square root of 2, 0 plus e to the power of e phi, state 1. So when I apply Hadamard to state 0, it creates state plus. And the Hadamard itself gets this 1 over square root of 2 factor 2. So I have 1 over 2, right? So here I have this state plus, then plus e to the power of e phi is just like it doesn't depend on this. The Hadamard gate doesn't affect this phase prefactor, and state 1 turns into state minus. So let's rewrite this in the 0-1 basis. So it will be 1 over 2. The state plus is state 0 plus state 1, then plus e to the power of e phi state 0, and then minus e to the power of e phi state 1. So far, so good. And now I group these terms with the same of the same state. It gives me this one, and this one, right? So it will be 1 plus e to the power of I phi state plus 1 minus e to the power of e phi state 1. Okay. So now I want to rewrite these two terms. How? Let me change the color, for example, to the blue one. So I have this 1 plus e to the power of I phi. So first of all, I phi is cosine phi plus e sine phi. So now what I want to do, I want to use the formulas for the cosine of double angle, right? So for the cosine phi, I can rewrite this as cosine square phi over 2 minus sine square phi over 2. And similarly, sine phi is 2 sine phi over 2 times cosine phi over 2. Is that right? Yeah, it looks right. And finally, for unit, unit is nothing but cosine square phi phi over 2 plus sine square phi over 2. So all this being plugged into this formula gives me cosine square phi over 2 plus sine square phi over 2 plus cosine square phi over 2 minus sine square phi over 2, and then plus 2i sine phi over 2 cosine phi over 2. So I see that these two can be cancelled out. These two give me 2 cosine. So it will be 2 cosine square phi over 2 plus 2i sine phi over 2 cosine phi over 2. So now I can factorize this by taking 2 cosine phi over 2 out from the parentheses, and here I get cosine phi over 2 plus e sine phi over 2. And well, this is nothing but the e to the power of I phi over 2, right? And the result, finally, the result for the first one is 2 cosine phi over 2 times e I phi over 2. Looks good. And for the second one, I mean, this is just the change of the sign in the parentheses. So it's 1 minus e to the power of I phi. So here it will be change of this sign here, right here. These changes will be the same, but this, oops, no, this minus here, and this minus was before cosine, so it will be minus here, then plus here, plus here, and also minus here. Right, so what I get, instead of canceling sine, I have canceling cosine square phi over 2. Right, so the result will be minus 2i, this minus here. All right, then sine phi over 2 e to the power of I phi over 2. Looks good. So now let's return to this one and plug in well, actually, let's write this as a as a state, because this is actually the final state that we after, right? The state psi and the output of this system, of this circuit. It will be what? It will be 1/2 and then 2 cosine phi over 2 e to the power of e phi over 2 state 0 minus 2i sine phi over 2 e to the I phi over 2 state 1. So we can take the we can take this 2 and e to the power of I phi over 2 out and cancel 2. So it will give me it will be e to the power of I phi over 2, and then this parenthesis cosine phi over 2 state 0 minus e times sine phi over 2 state 1. So now, according to the quantum mechanics, we have to, I mean, in order to find the intensity, right, of or normalization of this psi function, we have to take the inner product of these two, and this gives me the product of this term, phase factor e to the power of I phi over 2 times e to the power of minus e phi over 2, so it's just 1. So we can omit this. We call this global phase, global phase. So the global phase can be omitted. It doesn't affect the result at all. And for this result, we can now write this. We can parameterize this as C1 state 0 plus C2 state 1, where C1 is nothing but cosine phi over 2, right? And C2 is nothing but minus I sine phi over 2. I just rewrote this line and omitted this global phase factor. So what we obtained this the state of a qubit with projection coefficients C1 and C2, but now these projection coefficients depend on the phase that is provided. I just remind you, provided by this this phase gate in the circuit. So let's so according to the Born's rule, right, the result of the measurement of the qubit is given by the absolute value of the projection coefficient. And for example, for the C1 modulus square, it is cosine square phi over 2, which can be rewritten by, I mean, as this 1/2 1 plus cosine phi. And for the modulus of the coefficient C2, similarly, I obtain sine square phi over 2, which is 1/2 1 minus cosine phi. So this is the probability of state, state 0. So yeah, maybe I should change this indices. So it should be C0, and this one should be C1. Right, so it's a C0, C1, C0, C1. So it's a probability of state 0. This is probability of state 1. So the probability of finding the system in state 0, it's 1/2 1 plus cosine phi. Probability of finding in state 1, it's 1/2 1 minus cosine phi. So now we can return to our optical case in the beginning of the lecture, where it was. Here, right? So I refer to these formulas here for the interferometer. So these two results are exactly the same. So we conclude that. Oh, by the way, probably I should mention that the resonator like this in optics, we call this Fabry-Perot interferometer. In optics, this is Fabry-Perot interferometer. Like physically, it is just a slab of some dielectric, like slab of glass. Any slab of glass has two surfaces, two screens, right? The first and the second one, and any slab of glass is already an interferometer. So the system like this circuit is also interferometer. This Golden Single Qubit circuit is a interferometer, and it gets the special name, the name after Ramsey. This Ramsey Interferometer. Ramsey Interferometer. So I can also draw, I mean, what I expect from the experiment or simulation. I expect, for example, for the zero state, for the phase 0, I have 1, so my probability is 1, and then it oscillates like this from 1 to 0 and back to 1, depending on the phase. Okay. So now I guess it's instructive to go ahead and open the IBM Quantum Qiskit, right? So do you see my screen with the IBM Quantum?
Yes, we can.
Okay. So what I do here, I launch Composer. That's I practiced. So let's start. Let's create a new one. So we have just one qubit. So let's remove the extra ones and also one classical bus. So according to our algorithm, what I do, I create the superposition, putting the first Hadamard. It creates the perfect superposition of two states, state 0 and state 1. then my phase gate is this P, right? So for now it's set in the state P/2, so it didn't change like these probabilities. And then I close my superposition. Also didn't change the result. Now I can go to the specifications, the parameters of this gate, and vary this phase here. So let's suppose I want to, so I can multiply by any number here. So let's say my phase is equal to 0. Our result gives us that I expect my system, my interferometer, is like perfectly in the state 0. So I cannot detect state 1 in my experiment. All the photons, all the excitations come out in the state 0. And then I change my phase, for example, just a little, and it creates, so it suppresses the state 0 and increases the probability of state 1. It makes more and more, and in the phase Pi/2, it is a balance between the state 0 and state 1, and then I can of course increase it higher, and it increases the probability of finding state 1 and decreases the probability of finding state 0. And finally, in the case of pi, my probability of finding state 0 is vanishing, but probability of finding of state 1 is 100%. Of course, if I put the measurement, it won't be like, for example, in this case, it won't be like perfectly 50%. It will be just very close to 50% in one case, and in another case. So this measurement, this measurement creates this noise. It takes into account the quantum noise. As we already know, this simulator takes into account the measurement noise. And for this reason, by the way, I expect that in your homework and in your midterm exam, I expect that your results, the simulation of your circuits will be like different, just slightly different in terms of these probabilities, right? So you see these numbers, they can never be like exactly the same for all of you. So this is like my quantum protected way to check that you guys don't simply copy paste the works of each other. Quantum protection of homework, cryptography of homework. Anyway, so yeah, so as you can see, this IBM Qiskit demonstrates nicely this effect of superposition. And changing the phase, you can change the result. Change the result. Let's go back to the lecture. Yes, and this is called Ramsey Interferometer. And finally, let's discuss why it's so important. So why so important? Well, the answer is that it enables quantum parallelism in computation. It enables quantum Parallelism in computation. So if you remember in the very first lecture, when I gave you the like introduction, it was an interesting example of a maze, right? It was a maze with input and output, and then like very sophisticated maze with many directions, and we say that the classical computer would try all these ways one by one until it finally founds or not found doesn't found the output. But if you are a quantum computer, what you do, you create the input, and this input launches the waves in all particular directions, like simultaneously. And then these waves interfere in a way that just one correct way finds the way out. Like when you ever find yourself lost in a concave, in a cave, instead of running back and forth and trying all the like paths, you simply can stop and give a cry, right? Or in physical words, you launch a wave that propagates in all directions simultaneously and exploits all directions, all pathways in the same time. And this is actually what happens in the most of the quantum algorithms. So instead of like talking about each quantum algorithm, because of lack of time, we very quickly run out of time. I just want to discuss this point to give you an idea how it can work. So what happens is that in quantum computer you have multiple input qubits, Q1, Q2, Q3, etc., all the way up to Qn. And then you put the Hadamard gates on the first qubits. So this is Hadamard gates. You of course can entangle these qubits by putting the C naught gates, but this Hadamard gate is like essential. And then both like this. Oops, sorry. Do you guys hear me?
Yes, Professor.
Yeah. Okay, yeah. I worried that maybe my connection was lost. Okay, and then I put another Hadamard gates to close the superposition, and then these qubits evolved out. So I have this out qubits. And according to our like algorithm, I have to have something. Let's call this some function f, right? That can be also like controlled somehow. And this function f is, or black box. Sometimes for some algorithms, people call this oracle. It's connected to each of these qubits and changes the phase of all of them somehow, right? Yeah, and so this part opens up this, creates superposition. Then you have this phase part that operates this with the phase pattern of all the qubits. The qubits can be entangled also. And finally, this last part of Hadamard gates close the superposition. And pretty much a lot of quantum algorithms are based on this approach. Like, for example, that quantum Fourier transform. Quantum Fourier transform is like very close to this one. Or there is another like quantum phase algorithm that detects the phase of quantum state. Anyway, so again, what you basically like, what you often have in input, you have like these probabilities in the first. I mean, for the input qubits, I mean, typically they are in the zero state. So this is basically 0, 0, 0, 0, 0 states of the first qubits. But then you open up the superpositions, change the phase of different qubits, and close the superposition. And you do that in a way to achieve something like this: very small probabilities for like different qubits, but some particular qubit, something like this. And this is your answer. Oops, answer. So this is input, and this is answer. So I mean, a lot of people, like quantum software engineers, try to come up with different quantum algorithms that utilize this approach of interference, quantum interference, to achieve something like this. You have something in input, like equal distribution of probabilities in the input, but in the output for the given algorithm, it creates a like very sharp spike, and that spike is your answer. This is how it works. All right, do you have any questions to this part?
I have a question.
Mm-hmm.
Like if I'm giving the input to the Hadamard gate, for example, like n qubits, the output of the Hadamard gate should be 2 to the power n, right? Means we should have all the states at the output.
No, if you give, so what do you mean? No, so your input is, I mean, typically these input qubits all in the zero state. So this is just one realization, because I mean, typically when you turn on the computer, initially it's prepared in the all input qubits in the zero states, but the outputs, in output you also have n qubits, but these n qubits can be, I mean, usually they are in the superposition states, which is like a billion realizations, right? This is the, I mean, infinite number of realizations, because each qubit is like a superposition of two states, 0 state and 1 state. And on top of that, the qubits are or can be entangled, which means that your output is is a like tensor product of all the qubits. There are 2 to the power of n realizations. So if your output is like 50 qubits, then you have 2 to the power of 50 different combinations there. And the point is that exploring this wave nature of quantum mechanics and this quantum, which gives you this quantum parallelism, it's very close to this situation here. When different realizations, you don't know these realizations before you measure. This is just possibilities, but the beauty of this resonator, this interferometer, is that it takes into account, or in computational language, it computes all the partial waves simultaneously, all of them, infinite number of these partial waves, and sum them up. Yeah, but this is for just one, and in the quantum computer you have a bunch of them, and having multiple qubits, they can be entangled. So this entanglement makes your quantum computer is 2 to the power of n 2 to the power of n Hilbert space, right? The number of dimensions in your Hilbert space is extremely large. Yeah, so if no questions, let's change a gear and talk about something relative to what we discussed, but that has the applications in other areas of quantum technology. And I suggest to create another chapter. It will be chapter 4. And let's call this quantum communications. Quantum communications. Because I really want to discuss this part. Quantum communications. And the chapter 4.1, let's call this No Cloning Theorem. No Cloning Theorem. No Cloning Theorem. So in classical computing, we can take a state of a classical bit. Usually, it's just 0 or 1, right? This state of a classical bit. And we can clone it, meaning that we can measure the state of classical bit. And for example, physical realization of a bit would be just charging of some very, very small junction, right? And if there is a charge there, it is 1. If no charge, then it is 0. And this effect of charge can be measured without affecting the charge significantly. So the charge is there, it's not affected, but we can measure it. And for example, using those electrostatic type of measurements. And then we simply can clone this classical bit. We can create the same bit somewhere. For example, create this bit in the RAM, right, in the memory, for example. And in this sense, this corresponds to some cloning of the classical bit of information. Let's maybe write this down because it's maybe quite important. So in classical computing, in computing, we can clone a bit, and then, for example, send this clone to the memory, or proceed this somehow, whatever. In contrast, in quantum, we cannot clone a qubit. Why? There are, I mean, this theorem can be proven like rigorously using math, but in the end of the day, this is because, like, for example, for the classical bit, in order to clone it, we have to measure it, right? In quantum, we can measure a qubit, but after the measurement, the qubit collapses. You remember this postulate, right? Collapses to one of the possible opportunities, one of the possible allowed states. For example, if we're talking about a qubit, it is either 0 or 1. So it collapses to another state, and what you measure is not the state of the qubit. It is the state of the result of measurements. So you simply don't know this state, and on top of that, the measurement is changes the state of the qubit. So you simply cannot create exactly the same state, or you cannot clone the qubit because we have to measure it, because we have to measure it, and the measurement destroys the qubit. So, for example, let's consider this CNOT gate again. So for the CNOT gate, we have one qubit, another qubit. The first one is control, and the second one is target, right? And the logic of this 2-qubit gate is as follows. So if I have some state in the control, of course, control doesn't change. So I have the same state in the output. But my input, let's suppose I have input like Y. Then my output in the target qubit will be what? It will be X plus Y, right? So you remember this X, or I mean, if you don't know, let me make this aside. So this plus means simply if X and Y equal to 0, then the state, then the resulting state is 0, 0. right? If the state is 1 plus 0, so the state will be 1. Let me get state 0. This state will be 1. And finally, if this 1 plus 1, it gives you 2, but you return to 0, so it will be 0. This logic. So now let's consider a particular case when my y, the state of the target, is the 0 state. So in this case, my circuit is this state x here, the output is x. And then I have this 0 here. And what I will get in x, in the output of the target qubit, it will be x, right? Because whatever I add to the state x, I mean, whatever I add to 0, this x returns me x here. It doesn't change the result. So it looks like I had one x state in the input and got 2 state x in the output. So is this cloning? Is this cloning? So the answer is no, of course. And to answer, to demonstrate this, we should consider a general state of a qubit. General state of a qubit. So let's suppose I have the state psi as my x, which is some alpha state 0 plus beta state 1. Right. So let's check if I can clone this general state the same way. The same way. Let me return to this case just in a second, and exemplify what I'm saying, what I mean by this. So in the output, the state of 2 qubit is 0x, right? And x is either 0 or 1. And in the output from this CNOT gate, I get state XX, right? So this final state is the product of 2 states, product of x and x. So it looks like a cloning of state x. But I'm going to demonstrate you that it doesn't work for the state of arbitrary state of a qubit like this one. So let's form the state 0 and the state psi. So this is the state of 2 qubits. So it will be alpha, or the 0 and then alpha state 0 plus beta state 1. And the product of 2 will be alpha and then here 0, 0 plus beta 0, 1. Beta 0, 1. I remind you that I count the qubits from right to left. So this is my first qubit, this is my second qubit, right, from right to left. And this is always like this in this IBM cascade and etc. If you add new qubits, they add to the vector from the left, and you count the qubits from right to left. from right to left. So this is my state, right? And now I'm ready to apply the C0 gate to this state. And what I get? So my control is the first one, and my target is the second one. So the first one in the first term is 0, so I don't change the target. But for the second one, my control is 1, so I have to change the target, and I change this to 1, so I get 1, 1. So this is the state I obtained after C0. But look, this is not the product. This is not the product of state psi, right? The product of state psi would be 4 terms with because my psi is here. So this is not the product of 2 psis, and actually this is, I mean, this state reminds this Bell state. If alpha and beta would be 1 over square root of 2, it would be perfectly the first Bell state, this perfectly entangled Bell state. But this is not the case here. So let's conclude this part by saying that no cloning theorem. It is simply about it is not possible. This is impossible. Symbol to clone a quantum state. But what actually you can do with a quantum state? You can teleport it, but you can teleport the state. And this is what we're gonna discuss right now. So do you have any questions about this part?
No, Professor.
Very good. So maybe the last part that I have for you today, and maybe like very interesting one. I mean, at least I like enjoy this every time I read about this. So let's call this. So first of all, it's chapter 4.2, and let's call this shared randomness. Shared randomness. So at this moment, we introduce these 2 persons, Alice and Bob. Alice here and Bob. And let's suppose that at some point in the past, Alice and Bob created, they share 2 qubits, and at some moment in the past, they created the entangled state of 2 qubits. So they entangled 2 qubits and then like separated this or shared these qubits. So the state of these qubits is the first Bell state, for example. It will be 1 square root of 2 and state 0, 0 plus state 1, 1. So this is the important experimental fact that that says that let's say you created your entangled qubits, like when they were, like, for example, very close to each other, and then separated them. For example, you sent one to the Mars and this another one to the moon, for example. The important experimental fact is that the qubits still entangled. That's why I draw this like wavy line between the qubits. So the qubits still entangled. They don't lose this entanglement between them, regardless of like how long apart they separated. One can be at the Earth, another one can be sent to the moon, whatever. They still share the randomness, and this is cool because this indicates and by the way, this is like already proven experimentally, and a lot of technological concepts are based on this simple fact. And like, for example, this quantum cryptography, quantum teleportation, quantum computing, and other areas, they are based on this fact, like, significantly. And there was an interesting story behind this, that, for example, Einstein, he didn't believe in this fact. And he said that the qubits cannot be, like, for example, distinguished by, separated by a very long distance. Then what about the information, like the speed, the velocity, the largest velocity in nature, which is the speed of light, right? And this situation tells us that oh, this shared randomness is something that like happens faster than the speed of light. And but the point is that when we separated the qubits, there are no physical interaction between them. It looks like when we separated the qubits, we kind of created two versions of our universe, of our reality. And we don't know in which version of our reality we live before we do the measurement. This is mind-blowing, and I'm like very curious or very puzzled about how it looks like. But let's take it as a fact, like experimental fact, that this is work like this. So what happens next? So Alice and Bob, they share these two qubits, and the qubits are prepared in the Bell state, right? So then Alice does the measurement of her qubit, for example, in the basis 0, 1, in the basis 0, 1. She can choose another type of basis, but for now, for simplicity, let's assume she makes the measurement in the 0, 1. So what she can obtain in her measurement, right? So what it means to do the measurement, it means to take the inner product of these basis vectors and calculate the probabilities, right? For this simple state, we have only two options. So she can find the 0 state, and then after the measurement, so I apply this 0 state on this Bell state, 0 0 plus 1 1, right? So state 0 and state 1, they are orthogonal. So my second term vanishes, turns to 0, and I have only one term here left, which is 1 square root of 2 state 0. So once again, this is the qubit of Alice. So Alice does the measurement, and let's say she finds the result 0, and I'm estimating like or calculating what would be the result of the measurement at the Bob side. Once Alice does the measurement, this measurement destroys the entanglement. And what does the Bob's qubit get is this state, basically state 0. So this is state of the Bob's qubit. And now, if Bob does the measurement of his qubit, he will certainly get state 0 and no state 1. You see, because Alice obtained state 0 in her measurement, and vice versa. If, for example, Alice gets state 1, for the same reason, the state of Bob will be on. Bob will have only one option to get. Bob gets state 1. So Bob doesn't know the result of his measurement because he doesn't know what Alice gets in her result. But when Alice does her measurement and, for example, gets 1, then she certainly knows with 100% certainty that if Bob will measure his qubit, he will get his qubit in the state 1, in the same state, and never get state 0. I mean, of course, there is some noise and some level of uncertainty, but theoretically, it is like this. So if Alice gets 1, she knows that Bob will get 1. If Alice gets 0, then she knows that Bob will get 0 and not 1. So the result of the outcome of Alice's experiment affects the result of experiment of Bob. But of course, Bob doesn't know the result of Alice's state. And if he, like, the only way to figure out, to know what's Alice's state, Alice has to send him some sort of information, email, like, oh, Bob, I got the state 1, for example. And this email, of course, will fly from Alice's side to Bob's side with the speed of light. So you don't break this speed of light limit, right, in the information transfer. You're still restricted by the speed of light. But what you do, you, like, when you create this entangled qubit, it looks like, and we still don't know why, and this is just another, like, theory, or not theory, the picture. This is called multi-universe picture to describe the reality, the quantum, how this quantum mechanics actually, like, look like? Why we have this shared randomness, this entanglement between two qubits? This is just one way to explain this. It's like we create two different, slightly different universe, two like possible universe. And then when we measure the one of the qubits, we destroy this entanglement, and in this way we like choose the one of these possible universe. This might sound crazy, but this is how it looks like. I mean, this is how it works. Yeah, so basically we destroy the universe to send a bit of information. So what is the protocol for sending information this way? So let's suppose we have a number of entangled qubits. Something like this. So again, by these wavy lines, I denote these qubits entangled, right? And they initially all in the Bell state, non-separable states, or separable state of two qubits. And I have a number of them, a number of them. So let's suppose now, so this is my Alice, this is Bob. So let's suppose Alice now does the measurement and gets the state 1 here, state 0 here, the state 1 here, and the state 1 here, for example. Then she certainly knows that when Bob does the same measurement, he will get 1, 0, 1, 1. Right? But now, let's suppose Alice wants to send the string of information like 1, 0, 0, 1, for example. So then what she does after the measurement, she sees that, for example, this one is correct. This one is what she wants to transfer. This 0 is also correct. This 0 isn't correct, and this one is correct. So she get like one like bit of mistake, and she knows that Bob gets this mistaken result. So they need to correct this. So what she does, she in the time moment. So these measurements of Alice and Bob, they are like time synchronized. They do the measurement of the first or the second with some time lag, and this process is like very synchronized. And then she compares with the result, and as she detects the wrong digit, she like sends in a mail or sends the pulse, electromagnetic wave, to Bob, and Bob detects this pulse and decides that, oh, this qubit is wrong, and he has to change this digit to the digit 1. You see? And this way he obtains the correct result. So what's the point of this? The point is that the half of these operations, like when the result of the measurement corresponds to the information that Alice needs to send to Bob, when the result, I mean, this result and the string coincide, they the same. They don't need to share the correct bit. but when Alice detects the bit incorrect, and she sends this pulse to Bob in order to make him change this bit, right? The another person, we call him or her eavesdropper. So eavesdropper is a person who tries to get this information, because the information can be like a secret. So this code 1001 something, it can be like the code to your bank account, for example, with billions of dollars on your account, and eavesdropper wants to steal the money from your bank account, and and he needs to know this digit string, this digit number, and he kind of can, of course, connect to this line somehow. Well, not this one, right? To this classical account, this classical channel between Alice and Bob. This can be like wires or like optical fiber, whatever, some classical channel. What he can measure only like some pulses of electromagnetic field in some time moments. And he knows that, for example, Alice sends this pulse when the bit is wrong, but he doesn't know the result. He doesn't know the bit. What he gets just the times of moment, the moments of times when the bit is wrong, but he doesn't know the bit, so he cannot even guess the right number. And at the same time, if he somehow tries to get to this quantum channel, this he tries to eavesdrop the information from the quantum channel. This way he destroys the quantum channel, because the result of the measurement destroys the superposition and entanglement. So he can measure something, right? But when he measures this, Bob immediately see that, he may immediately detect this in his results of measurement, and Alice see that in her results of measurement, because of this no cloning theorem. For example, one would say, oh, eavesdropper can measure the quantum channel and then prepare exactly the same state and send this to Bob, but he cannot do that, because he cannot clone the quantum state. And this is the like a hint how the quantum cryptography concept works. So eavesdropper cannot get information from the classical channel, and any try of getting information from the quantum channel immediately destroys the quantum superposition and breaks. Eavesdropper cannot get information from there. On top of this, for example, if you have, if Alice has many qubits to measure, as we saw many times, the probability of finding 0 and 1 is almost like 50%, right? But if eavesdropper gets into this quantum part of this circuit, Alice will immediately detect that by observing the change in the probabilities. So her probabilities will change, and then Alice conclude that there is something that tries to get information from the channel. And this is quantum cryptography, and we're gonna talk about quantum cryptography next time. And yeah, and this is it for today. Do you have any questions about this part before we maybe discuss the formal things?
No, Professor.
All right, very good. So then let me stop the recording.